Okay, we have the notes for section 4, building functions from functions. So a couple definitions up here at the top. The sum, difference, product, and quotient rules. The one thing you have to be careful of is on the quotient. Since you have a denominator, the denominator cannot be equal to 0, otherwise it's unsolvable. It says in each case, the domain of the new function consists of all numbers that belong to both the domain in f and the domain of g. As noted, the zeros, the denominator, are excluded. So that means up here. So example 1. Let f of x equals x squared and g of x equals the square root of x plus 1. Find the formula for the functions f plus g, f minus g, f times g, f over g, and g times g. Give the domain of each. So f plus g is add the two functions together, so x squared plus the square root of x plus 1. Now this has a square root, so for the domain for this one, the stuff underneath the square root must be greater than or equal to 0. So x must be greater than or equal to -1. F minus g, x squared minus the square root of x plus 1. So same domain, I'm not going to do the work again, but pull the stuff underneath the root out, set it greater than or equal to 0. Let's see, the next one is f over g. So that's x squared over the square root of x plus 1. So the domain for this one has this guy because of the root. Also, I have to check this because I have a fraction. So x plus 1 not equal 0, square both sides. So x can't equal -1. So if you actually put these two things together, your domain is actually just x is greater than -1. Whoops, I went out of order. I missed f times g. So that's x squared times the square root of x plus 1. So same domain, because I have the root, I get that guy. It's the same work as that. So I did plus, did minus. So I need to do now g times g. So gg is going to be root x plus 1 times root x plus 1. So since I once again have the roots, the domain is the same as it was before. All right, so there is actually one other operation that you can do on functions that's referred to as compositing. If you composite a function, you plug one function into another. So this picture here kind of illustrates what's happening. So you take some value of x, plug it into g, and that gives you some value out. And then you take that value and plug it into f, and that gives you f of g of x. So some number x is plugged into g, and then that whole value gets plugged into f. So f of g gets you all the way across. Okay, so example 2, let f of x equals e to the x and g of x equals root x. Find f of g and g of f, and verify that the functions are not the same. So f of g means plug the g function into the f function. So there's g, root x, I'm going to plug it into f. So instead of that, I'm going to have that. So what happens is this entire equation replaces that x. The reverse, g of f, is backwards. Let's take the entire f equation and plug it in for the x and g. So instead of root x, I have root e to the x. So it says verify numerically the functions are not the same. So we'll set x equal to 1. So this is e to the root 1. This is the square root of e to the first. So this is just e, and this is root e. So these two things are not equal. So the functions are not the same. So example 3, let f of x equal x squared minus 1, g of x equals root x. Find the domain of the composite function g of f and f of g. So g of f, plug f into g. So root x squared minus 1. And then f of g is the reverse, that into that, so it's the square root of x squared minus 1. So here I have a root, so the stuff underneath the root must be greater than or equal to 0. So x squared must be greater than or equal to 1. So I have to take the square root of both sides. When I do that, I get the positive solution, and I get the negative solution. So these two things must be true, more than 1 or less than -1. Over here, I just have, just a single root. So the stuff underneath must be greater than or equal to 0. And that's already solved. There's nothing else to do. Okay. Example 4, for each function h, find the functions f and g so that h of x is equal to f of g of x. So we're undoing the stuff we did before. So we have some function f of x. We have some function g of x. So g of x is what got plugged into f of x. The easiest way to do this is to look for grouping symbols. So parentheses are grouping symbols. So g of x is just going to be x plus 1. Now to undo it, if I pull the x out, I'm taking the grouping symbols away, but if you remember when you composite, you plug one function into the x's of the other. So that means in my original equation, f, wherever there was an x plus 1, just becomes an x now. So this is x squared minus 3x plus 4. So if I take this x plus 1 and put it in for these x's, I get my composite function back. So down here, some function f, some function g. Now there are no parentheses here, but the square root acts like a grouping symbol. So g of x is x cubed plus 1, the thing inside the grouping symbols. And if I pull all of that out, this just becomes root x. So whatever I take out, I have to replace back with that original x. Okay, example 5. In the medical procedure known as angioplasty, doctors insert a catheter into a heart vein through a large peripheral vein and inflate a small spherical balloon on the tip of the catheter. Suppose the balloon is inflated at a constant rate of 44 cubic millimeters per second. Find the volume after t seconds. So the volume of a sphere is 4/3 pi r cubed. Where was I? Suppose the volume is concentrated at 44. Oh, whoops. I don't need that. So that's how much is being inflated. So the volume is equal to 44 times t. So 44 cubic millimeters in times the number of seconds. Well, the volume is v. What is the radius r? This is where I need this formula. So I need to solve for r. So I need to put the 4/3 across. So to get rid of a fraction, you multiply by its reciprocal. So this becomes 3v over 4 equals pi r cubed. Divide both sides by pi. So this becomes 3v over 4 pi equals r cubed. And then take the cube root of both sides. See that. All right, so write equation, that should be an equation that gives the radius of r as a function of the time. So I need to plug this equation in for that v. So r equals the cube root of 3 times 44t all over 4 pi. And then what's the radius after 5 seconds? So that means just plug 5 in for t. And that's all numbers, so that can all just go in your calculator. So let's see here. We have 3 times 44 times 5 divided by 4 divided by pi. And then I'm going to take the cube root of that number, and out should come. The radius is 3.7 millimeters. All right, and the last topic for this section is implicitly defined functions. So if you have a set of ordered pair xy, that's referred to as a relation. If the relation happens to relate a single value of y to each value of x, then the relation is also a function, and the graph will pass the vertical line test. In the case of the circle, with the equation x squared plus y squared equals 4, both 0, 2, and 0, negative 2 are in the relation, so y is not a function of x. If you notice, the x values repeat with different y's, so that's what makes it not a function. So example 6, determine which of the ordered pairs are in the relation defined by this equation is a relation of function. So in order to do that, I just need to plug these xy pairs into my formula. So for example, for this one, it's going to be 2 squared times negative 5 plus negative 5 squared equals 5. For this one, 1 comma 3, it's going to be 1 squared times 3 plus 3 squared equals 5. And over here, 2 squared times 1 plus 1 squared equals 5. And I need to work these out. So that's 4 times negative 5, so that's negative 20, plus 25 equals 5, so 5 equals 5. Yes, that points in the relation. Over here, 1 times 3 is 3, plus 9. So this is 12 equals 5, so that is no. That point does not lie on the relation. And this one is going to be 2 times 1 is 4, plus 1 is 5, so 5 equals 5. Yes. Is relation a function? No. Because I have 2 points here and here, 2, negative 5, and 2, 1, which both are in the relation, but they use the same x value. So it failed the vertical line test. So this next one shows how you can split your function apart. So x squared plus y squared equals 4 isn't a function, but if I solve it for y, I get 2 equations that when put together will give me the same graph, but individually are functions. So this is referred to as implicitly, because these two equations together make up this one. So example 7, describe the graph relation x squared plus xy, 2xy plus y squared equals 1. So I need to solve or factor that, since it's x squared. We skip a step. We'll show it all. So to make x's, I need x and x. To make y, I need y, and add them up. Now this 2 happens here because if you do the FOIL, there's my x squared firsts. There's my y squared lasts. But when I do my insides and outsides, outsides first, that gives me xy. Insides also gives me xy. So that's 2 xy's. So since I have 2 identical parentheses, that's equal to the parentheses squared, then I need to take the square root, which gives me that. Now please notice there's a plus minus symbol over here, because when you take the square root you get 2 solutions. So we'll write them separately here. So I need to subtract the x across. So y equals positive 1 minus x, and y equals negative 1 minus x. Use the positive root and the negative root, and then subtract the x across. So those 2 lines describe the graph of the relation. If you plot them, they're actually 2 parallel lines. This one is the top one, crosses that positive one. The bottom one crosses that negative one. So that graph would graph 2 parallel lines. And that is the end of this section.